Look up at the night sky. It's dark. Obviously dark. You've never questioned it. Why would you? But if you did the math seriously on a universe that's infinite, unchanging, and full of stars, the night sky shouldn't be dark at all. It should be as bright, everywhere as the surface of the sun. No gaps, no black space between stars, just a solid wall of light, day and night, forever. That's not a metaphor. That's actual physics, done rigorously centuries ago. And the fact that you're not currently blind from staring at the sky is one of the strangest puzzles in the history of science. The question is called Olbers' Paradox, named for the German astronomer Heinrich Olbers, who formalized it in 1823. Most people's first instinct is simple. Distant stars are just too dim to see. That seems obvious. Light fades with distance, case closed. Except it's wrong. And the reason it's wrong is genuinely elegant. Yes, an individual star gets dimmer the farther away it is, following a strict rule. Brightness falls off with the square of the distance. But here's what that explanation misses. As you look farther into space, you're not just seeing fewer, dimmer stars. You're seeing exponentially more of them. Because the volume of space at each distance increases just as fast, the math works out so that the dimming of individual stars and the increasing number of stars exactly cancel out. Every shell of space around you, no matter how far away, should contribute the same total amount of light. Add up infinite shells in an infinite universe, and you get infinite light. Every single point in the sky should eventually hit a star. Too dim to see doesn't hold up. The math says otherwise. Olbers himself knew this and proposed his own solution. Space must be filled with dust, blocking the distant starlight. It sounds reasonable. Dust absorbs light. Problem solved. Except it isn't, and it took decades for anyone to prove exactly why. If dust is absorbing all that starlight over the lifetime of an infinite, unchanging universe, it would have to heat up. And once it got hot enough, it would start glowing itself, radiating the exact same amount of energy it absorbed. The dust wouldn't dim the sky. It would eventually just become another source of light. Olbers' own fix didn't survive contact with thermodynamics. The paradox stayed unsolved for decades. Here's the part almost nobody knows. The first person to stumble onto the real answer wasn't an astronomer. It was a writer, better known for horror stories than physics. In 1848, Edgar Allan Poe published a strange, sprawling prose poem called Eureka. Buried inside it, almost as an aside, Poe proposed something remarkable. He suggested that if the universe had a beginning, if the stars hadn't been shining forever, then light from the most distant stars simply hasn't had time to reach us yet. A dark sky, he argued, wasn't evidence of absence. It was evidence of a horizon. A poet had essentially guessed the correct resolution to a physics paradox, decades before physicists caught up. It took until the 20th century for cosmology to catch up to Poe's instinct. The universe we now know is not infinite in age. It began roughly 13.8 billion years ago. Light travels fast, but not infinitely fast. That means there's a hard limit on how far we can possibly see. The distance light has managed to travel since the universe began. Beyond that boundary, called the cosmic horizon, there could be infinite stars. It wouldn't matter. Their light literally hasn't had time to arrive yet. On top of that, the universe is expanding, stretching the light from distant, receding galaxies into longer wavelengths, draining away some of its energy before it even gets here. Between the finite age of the universe and its ongoing expansion, the math that once demanded a blindingly bright sky simply breaks down. The night sky isn't dark because there isn't enough light out there. It's dark because most of that light hasn't reached us yet, and some of what has been stretched into wavelengths we can't even see. So the next time you look up at a clear night sky, look again at what you're actually seeing. Not empty space, not absence, a boundary. The literal edge of how far light has traveled since time itself began. Every dark patch between the stars is a place where the light is still on its way, still crossing 13.8 billion years of empty space, headed toward a planet that, for now, is still waiting in the dark.